Hello everyone, I am Faranjam from Sri Venkateshwara College of Engineering, Bangalore. The topic for today's presentation is CephArmor, a lightweight cryptographic interface for secure high-performance Ceph storage systems from the course Cryptography and Network Security. Abstract. The study addresses security vulnerabilities in Ceph, a widely adopted storage system, particularly concerning data confidentiality. It proposes CephArmor, a lightweight API that enables object encryption on storage devices, thereby mitigating data leakage risks. The API simplifies encryption processes for users while ensuring data is securely maintained in an encrypted format. The experimental results denote an overhead regarding elapsed time, throughput, average operations per second, and latency on a write operation. In contrast, the read operation illustrated near zero performance overhead for the same metrics. Introduction. Clustered storage systems provide suitable solutions for data-intensive applications like multimedia and meteorology, but cloud storage, although straightforward, is costly and not always favored by governmental organizations due to privacy concerns. Ceph is an open-source distributed storage solution designed to address scalability, single point of failure, and performance issues in storage systems, making it suitable for high-performance computing, data centers, and cloud environments. Ceph offers various storage types through its reliable, autonomous, distributed object storage layer, including block storage, RADOS, block device, and file storage through CephFS. The Ceph community has emphasized improving metadata management and file system load balancing to enhance system capabilities, while security aspects like data confidentiality have been less prioritized. Although Ceph includes authentication and access control, it lacks built-in support for data confidentiality at storage devices, relying instead on external solutions like LUKS or client encryption, which can introduce complexities and potential vulnerabilities. Problem statement. NIST outlines 5 core security objectives: confidentiality, integrity, availability, authenticity, and accountability, emphasizing a comprehensive approach to security network connected systems. Despite the NIST recommendation, Ceph primarily focuses on authentication and access control, lacking its built-in mechanisms for data confidentiality, making it vulnerable to data theft if authentication is compromised. Common security threats to authentication include social engineering, brute force, session hijacking, keylogger attacks, and SQL injection, which can lead to unauthorized access and compromise data confidentiality. Data encryption is essential for protecting information against unauthorized access. However, Ceph does not provide native encryption at the storage layer, relying on client-side encryption through the RADOS gateway interface, which introduces complexities in key management. To address the confidentiality gap, the study suggests implementing an embedded encryption approach within Ceph to enhance security at the storage layer, making data less vulnerable to unauthorized access. Contribution. CephArmor is a lightweight security API designed to provide data encryption over the RADOS layer in Ceph, ensuring data confidentiality without impacting performance. The API integrates storage encryption directly into the Ceph source code and offers a user-friendly comprehensive security solution suitable for both professional and non-professional users. The proposed method has been deployed in a real-world environment with extensive experiments and benchmarks conducted to assess its performance and effectiveness. System overview. Ceph background. Ceph's architecture includes key components like object storage daemons, monitors, manager data server, and metadata servers. RADOS forms the core storage layer with OSDs and MONs being critical for enabling Ceph's storage services. Ceph offers 3 main communication interfaces, all built on the RADOS layer. The library supports high-speed communication through socket-based protocols, while the RADOS gateway facilitates REST-based object storage, and RADOS block device provides block storage for cloud environments. RBD is used for creating block storage units in virtual machine environments, while CephFS provides a POSIX compliant file system for hierarchical storage. These components leverage the RADOS API to interact with OSDs and MONs for data management and storage in the cluster. A review on block encryption techniques. Symmetric encryption uses a single key for both encryption and decryption, while asymmetric encryption uses separate keys for each process. Symmetric methods are faster, while asymmetric ones are better suited for secure key exchanges, especially in multi-user environments. AES is a symmetric block cipher with 3 key lengths, 128, 192 and 256 bits. It is known for the balance of speed and security, with AES 128 being effective against most current threats, while AES 256 provides additional security, particularly against post-quantum attacks. AES uses substitution permutation operation on 128-bit data blocks involving stages like XORing, substitution, and permutation. Each stage transforms plain text into ciphertext using the key, providing secure encryption. In the AES CBC encryption, each block of plain text XORs with the cipher resulting from the previous encryption block's cipher I-1 and encrypted by the secret key K. An initialization vector denoted by IV is generated at the beginning of encryption to fulfill the algorithm's primary requirements, as there is no previous plain text block as seen in the equation. The decryption, however, has no dependency on any process from other blocks. In decryption, the plain text block plain I resulted from XORs of the current decrypted block cipher I by secret key K and previous cipher block cipher I-1, which are prepared in advance. Similarly, the IV at the beginning of the process accomplishes the algorithm requirement as seen in the equation. AES 128 is time efficient but may be vulnerable to future quantum computing capabilities. AES 256 offers greater resistance but comes with a 40% overhead compared to AES 128, making it more suitable for high security needs. System design and implementation. Threat model. Malicious actors can be internal or external. The proposed system requires mandatory authentication to access key functionalities, unlike Ceph's optional authentication. The system offers two modes: CRC mode, where data is encrypted by CephArmor but after being sent as plain text, and secure mode, which encrypts data end-to-end during transmission, ensuring stronger data protection. Ceph maintains data availability through replication and erasure coding with a self-healing feature to restore lost data copies. However, it lacks mechanisms to detect unauthorized data modifications, assuming an honest but curious model where storage systems do not alter data. AES encryption is considered robust against known attacks, with the security of the key management system assumed. Design. The CephArmor API consists of three main components: CephArmor, Crypt, and KMS. For a write request, CephArmor verifies user authentication, requests an encryption key from KMS, encrypts data using the Crypt model, and stores it across OSD nodes. For read requests, the process is similar but includes decrypting the retrieved data before returning it to the user. In replicated mode, encrypted data is copied across OSDs. In EC mode, the data is split into chunks with parity and distributed. Regardless of the pool type, only one encryption or decryption operation is required per request. Cryptographic operations use AES via OpenSSL implemented in C++ to ensure high performance. The API components are designed to remain independent of Ceph's core code, facilitating easier updates and maintenance. KMS securely manages cryptographic keys using user passphrases and hardware security models for secure storage. Communication between CephArmor and KMS is encrypted using TLS, ensuring confidentiality and integrity of the exchanged information. Experiments. The experiments in this study are conducted using 3 server nodes with commands sent through SSH connection to simulate a real-world environment. A single KMS manages the lifecycle of encryption keys, providing keys and initialization vectors for encryption or decryption. Key evaluation metrics include storage overhead, execution time, bandwidth, IOPS, and average latency. Evaluation tool. Ceph includes internal performance evaluation tools through APIs like REDOS and RBD, which allow for the analysis of read or write operation using various parameters such as the number of threads, message size, and objects. An additional benchmark component has been integrated into the CephArmor API, especially for evaluating encryption or decryption performance. To conduct read performances benchmark, sufficient objects must be stored in the cluster beforehand, as a write operation is required to create these objects. The benchmarking process involves generating a metadata file that tracks benchmark information, and it also allows for parameters to prevent object removal after write evaluations. Cluster environment. Experiments evaluate replicated and erasure-coded pools, demonstrating that performance improves with the number of data chunks due to parallel processing, while the replication size indicates fault tolerance. Then 3 monitors overseeing the storage operations across 64 placement groups. Results. This figure illustrates the results of the single and multi-thread write experiments. The cryptographic process and Ceph's underlying algorithms significantly influence storage performance. The encryption process relies on sequential dependencies which extend storage time, while decryption can occur in parallel across submodules, enhancing retrieval speed. The crush algorithm manages object placement based on replication domains, optimizing performance when all copies are stored on a single server, thereby minimizing network communication. However, the inability for users to configure these complexities and the impact of mapping placement groups across different network servers further complicate performance outcomes. Conclusion. CephArmor is a lightweight and secure API developed to enhance data confidentiality in Ceph by encrypting data on OSDs and thereby reducing vulnerability to unauthorized access. It allows users to perform object encryption and configure algorithms and key strengths without dealing with the complexities of the underlying system. Integrated with Ceph version 16.2.7 and tested in a commercial environment, experiments showed that while write operations incur some execution time overhead, increasing concurrency levels effectively mitigates this impact. Read operations displayed minimal overhead due to quicker decryption times, with future research planned to further optimize encryption times during writes without compromising security. These are the references of the research paper. Thank you for watching the video.